Good day, students. This is the MYA Review Part D transformations. At this time, you should have logged into the quizzes lesson and put in the code so you can follow through with the review. Please make sure that you have also your long-term memory review pulled up in the OneNote class notebook, so that way you can refer back to the notes that were placed on that page. All right, so back in topic 1, we talked about transformations, and as you can see, there are 4 different types of transformations. So we have a translation, and a translation we know is also a slide. It takes one object and slides it from vertex to vertex to create another figure. We also have a reflection. A reflection is also known as a flip. So we're taking the object and flipping it over some type of line of reflection to create the image. As you can see with a reflection, it changes the orientation or direction of that figure. The next one we have is a rotation. A rotation we also know is a turn. So we are taking the image or the object that we have, and we are turning it about some type of given angle to create now a new image. Also, once again, a rotation changes the orientation or direction of a figure. And lastly, we have a dilation, and a dilation can either enlarge or reduce the size of a figure. So it can either make it bigger or smaller depending on the scale factor of the dilation that's given. Of the 4 different types of transformations that we have, we can break them out into 2 categories: rigid transformations and non-rigid transformations. Rigid transformations does not change the shape or size of a figure, and that figure is the pre-image or the image. So the pre-image to the image will remain the same. The 3 rigid transformations that we have are reflections, rotations, and translations. Non-rigid transformations can change the shape or size of a figure of both the pre-image and image. The non-rigid transformation that we are focusing on are dilations. So when a transformation has taken place, we generally identify the images as the pre-image and the image. So the pre-image is the figure that you originally start out with, so your original image. And you can identify your original image by the notation that you have for each of the vertices of the figure. So they are normally identified with capital letters at each vertex. The image is what you have after the transformation. So this is after transformation. So you are able to identify the image by these notations next to the capitalized letters, which we call prime. So these notations are called prime notation. So when we transform a figure, we start with the pre-image, and this little symbol here means map to the image. So I'm taking my pre-image, applying some type of transformation that's going to map my pre-image onto my image. So at this time, we're going to start looking at some examples of transformations. Right now, you can pause the video and try the next couple of problems and come back to see if you got those questions correct. Okay, welcome back, and let's look at this first question. It says a transformation of a polygon that always preserves both length and orientation is called a translation. So the key term in this question was the word orientation. Orientation pretty much means position. So when I translate a figure, so say if I have this triangle, and I translate this figure, a translation is also called a slide. So when I slide this triangle in whatever direction, it does not change the orientation of the triangle. The triangle still remains upright in the same position. As far as a rotation or a rotation and reflection changes the orientation of the figure, therefore changing the direction. Let's look at number 2. In the accompanying diagram, which transformation changes the solid line parabola to the dotted line parabola? Well, looking at this figure, the first one would be considered what we would call our pre-image. And then the second figure that we would have here would be our image. Now, looking at the pre-image to the image, I see that there are possibly 2 ways that I can transform the pre-image to the image, or map the pre-image onto the image. The first way would be to reflect it across some type of reflection line at the vertex of both of the parabolas. So that means that I'm flipping the parabola over the line of reflection. And this yellow line would be that line of reflection. The second thing that I could do is possibly rotate the parabola to the left or to the right to map that pre-image onto the image. So another way would be to rotate, or do a rotation of that figure. Here the next problem says, in the accompanying diagram, triangle ABC is similar to, but not congruent to, triangle ABC, A prime, B prime, C prime. Which transformation is represented by triangle A prime, B prime, C prime? So the key word here was similar, but not congruent to. So if I know that I have a transformation that's taking place, and it's not congruent from the pre-image to the image, then I know it is not a rigid transformation. It would have to be a non-rigid transformation. And the non-rigid transformation that we discussed earlier was a dilation. I can confirm that it's a dilation because my pre-image is much smaller than my image. We know that rigid transformations preserve the length and the size of a figure. So now that we've looked at the general definitions of what rigid and non-rigid transformations are, let's look at each individual rigid transformation and their definition. So here we have translations. So remember, we stated that a translation is a slide. So when I slide a figure, there are 4 different ways where I can slide a figure. I can slide a figure to the right, and if I slide a figure to the right, the function notation would be to slide that figure along the x-axis, where I would add some type of unit, and A would be that unit. If I slide that figure to the left, that means I am subtracting some number of units along the x-coordinate from x. Next, if I wanted to slide that figure up, I would add B units along the y-axis, and I would be adding B to y. And then if I wanted to slide that figure down, that means I would be subtracting some B units along the y-axis, where I subtracted B from y. Next, we have reflections. So there are 5 different types of reflections that take place. I can reflect about the x-axis, and with the x-axis, I see that my pre-image changes only with the y. So if I reflect along the x-axis, my y becomes opposite. Don't like to use negative. It just becomes the opposite sign. If I reflect my pre-image along the y-axis, my image now has an opposite x. If I reflect my pre-image about the y equals x line, then my pre-image now has flipped. Oops. My pre-image has now flipped. So that means that my x becomes y and my y has become x. If I reflect about the line y equals negative x, not only do I flip my image, but my signs are now opposite for both my x and y. And then, of course, if I reflect about the origin, the only thing that happens is that my x's and my y's become opposite. The last rigid transformation that we have is the rotation. So, rotating 90 degrees clockwise. Remember, going clockwise means that I'm moving to the right. Think of yourself on a clock. Clockwise, moving to the right. Not only do I flip my coordinates, I also take the opposite of the x. Remember, rotating 90 degrees counterclockwise means I'm moving to the left. So when I move to the left, I flip my coordinates, and now my y becomes opposite. Rotation of 180 degrees. So remember, rotating 180 degrees means that I can go left or right, and that's the same direction. Rotating clockwise or counterclockwise is the same direction for 180 degrees. I don't flip, but my signs become opposite for x and y. Rotating 270 degrees clockwise, remember clockwise is going to the right. I am flipping my coordinates and my y becomes opposite. And then rotating 270 degrees counterclockwise means I'm going to the left. Once again, I flip and my x coordinate becomes opposite. So at this time, ladies and gentlemen, we're going to be going over 3 problems in this section that's going to be focusing on applying the transformation rules for translation, reflection, and rotation. So at this time, you might want to pause the video so you can go ahead and try out the next 3 problems and then come back to see if you were on the right track. Okay, welcome back, guys, and let's go ahead and look at the 3 problems. So the first one says, on the set of axes below, pentagon ABCDE is congruent to A prime, B prime, C prime, D prime, E prime, which describes a sequence of rigid motions that maps the 2 pentagons onto each other. So the first thing that I need to do is identify, excuse me, which one is the pre-image and which one is the image. So as we stated before, the pre-image is always the figure that has the capital letters without the prime notation, and our image is the ones with the prime notation. So when we're looking at this type of problem, we always want to first look at the orientation of the figure. Has the figure changed its orientation or has it remained the same? In this case, we see that the orientation has changed. I see that my C is pointed straight up, and then the C prime and my image is now pointing to the left. So that tells me that some type of turn has taken place. If a turn has taken place, that tells me it's been a rotation. So this figure has been rotated a certain amount of degrees. I always like to focus on one point of the figure and guide that point up until we get to our image to see what type of transformation took place. So we're going to look at point A. Point A we have as 2, 2. And I need to know what type of rotation actually took place. So we always rotate from the origin, and the origin tells us that if we rotate it 90 degrees, we rotate 90 degrees making a right angle from the origin to point A. From the origin to point A. So from the origin to point A is a 90-degree rotation. So if I rotate that 90 degrees, and if I'm rotating, I'm going 90 degrees counterclockwise because I'm going to the left. Remember, the rule says I flip and take the opposite of y. So if I flip and take the opposite of y, my point A is now going to end up here. So that means I have a new A, And if I flip and take the sign, opposite sign of y, I have negative 2, 2. So now that I have my new point here of A, now I have to make sure that I can find another transformation that's going to move point A to A prime. So what I notice is that from A to A prime, it looks like a slide has taken place. So that means that I have a translation. It looks like a translation has taken place. So that means I am translating or moving A in the downward direction. So the current point that I have here for A is negative 2, 2. The point that I'm trying to get to for A prime is negative 2, 1, 2, 3, 4, 5. So negative 2, negative 5. All right? So that means what rule took place in order for me to move from the original point to now the new point? Well, I see that my x remained the same, so nothing happened with my x. But I did move my y. But I need to determine how many units did I move it. So it looks like I moved 1, 2, 3, 4, 5, 6, 7. And I moved 7 units down. So if I move 7 units down, that means from my y, I am subtracting 7. So the rigid motion, the sequence of rigid motions that's taken place with this problem is that I rotated 90 degrees counterclockwise, and I translated 7 units down. Okay, the second question states the coordinates of trapezoid ABCD are A, negative 4, 5, B, 1, 5, C, 1, 2, and D, negative 6, 2. Trapezoid A prime, B prime, C prime, D prime is the image after the transformation rule reflection across the x-axis and a reflection across the line y equals x is performed on the trapezoid ABCD. We need to state the coordinate for B prime of the trapezoid. So basically they're telling us that two transformations has taken place. The first one is a reflection across the x-axis, and then the second one is a reflection across the y equals x line. And we are focusing only on the B coordinate. So if I look at the transformation for the reflection across the x-axis, I know that rule tells me if I take a pre-image, that pre-image is going to be transformed by keeping my x coordinate the same, but taking the opposite of my y. And then reflection across the y equals x line tells me my pre-image is now going to flip positions. So my x becomes my y and my y becomes my x. So if I am looking only at my B coordinate, which is 1, 5, I'm going to apply these two rules. My first rule tells me to keep my x coordinate the same, which is 1, but take the opposite of my y, which is negative 5. And my second transformation, which leads me to B prime, tells me that I now flip my x and y. So now my x becomes negative 5 and my y becomes 1. And ladies and gentlemen, that is my answer for B prime. All right, so this is the last one in this set. It says in the diagram, congruent figures 1, 2, and 3 are drawn. Which sequence of transformations map figure 1 into figure 2, and then figure 2 into figure 3? So once again, we are trying to identify what sequence is taking place from our pre-image to our image. And we notice that this figure number 1 obviously is our pre-image, and this final figure over here, number 3, is our image. So just looking at the three figures, the first thing, like I stated before, in the first problem is that we need to look at the orientation from one figure to the next. So I notice from figure 1 to figure 2, the orientation has not changed. Just the position has changed. So if I just look at one point, and let's focus on point D, I see D has moved some units to the right, and then some units up. So that tells me that the first transformation that has taken place is some type of translation. If I look at the second figure to the third, the second figure to the third, I see D is here, and if I look from the origin, or if I look at the two figures from 2 to 3, I see the orientation has changed. A is sitting upright, and now in figure 3, A is to the right. So that tells me some type of rotation has taken place. So if I look at from the origin, I see I have some type of rotation, and it looks like that rotation is going to the right. So some type of clockwise rotation. So that would have to be my second transformation that has taken place. So let's go ahead and continue to the next part of our review, which is on reflectional and rotational symmetry. So reflectional, or what we sometimes call line symmetry, is when we reflect a regular polygon across a line of symmetry, and that carries the polygon onto itself. So when you see this word regular polygon, that means it has congruent sides. So all of the sides are the same. And polygon just means you have many sides. Okay? So a polygon could be a triangle, a quadrilateral, pentagon, hexagon. It's just a figure with many sides. So when I have some type of line symmetry, that means I can take that figure and fold it along itself, depending on the number of lines of symmetry it has. So that way it maps onto itself, or as it says, carries a polygon onto itself. So as you can see, we have one line of symmetry here for the letter T, two lines of symmetry for the letter H, and then no lines of symmetry for the letter F, because there is no line that can be drawn through F that will create this F to be mapped equally onto itself. The letter D has one line of symmetry that can be folded over, and then a circle has infinitely many lines. So it doesn't matter how many lines I draw through the circle, as long as that line is being drawn through the center of the circle, it has infinitely many. And once again, this last triangle that we have here, it kind of looks like a right triangle, but there is no line of symmetry that I can draw through this triangle that's going to allow me to fold it onto itself, to map to itself. Now we also have rotational symmetry. So rotational symmetry is when we rotate a regular polygon, and remember, regular means we have congruent sides, by a multiple of 360 degrees by n. N is the number of sides, and that will carry the polygon onto itself. So as you can see here, we have a figure that has 1, 2, 3, 4, 5, 6 sides. So a six-sided figure we know is a hexagon with 6 sides. And this is what we would call a regular hexagon because all of the sides are the same. If I take that hexagon and I divide the number of sides into 360, well, I get 60. 60 represents the number of angles, or the amount of times that I can rotate this figure about its center that's going to allow me to carry the figure onto itself. So that means the order in which I can rotate this figure onto itself would be 6, because I can turn it 6 times. And the degree that I can turn this in order for it to map onto itself would be 60 degrees. Now, as you can see, this figure right here has no rotational symmetry because first, it's not a regular polygon. The sides are not equal to each other. So therefore, it has no rotational symmetry. So once again, we're going to look at 2 problems that deal with rotational and reflectional symmetry. At this time, go ahead and pause the video so you can work out these 2 problems on your own and come back to see if you were on the right track. Okay, so the first question says a regular pentagon is shown in the diagram. If the pentagon is rotated clockwise around its center, the minimum number of degrees it must be rotated to carry the pentagon onto itself is blank degrees. All right, so once again, we have a pentagon. It's being rotated by its center. And remember, it's regular, so that means all the sides are congruent to each other. So that is the perfect classification of using these 360 degrees by the number of sides. So we know that we have 360 degrees, and we're going to divide it by 5. If I divide 360 degrees by 5, I get 72 degrees. So that means each of these angles here, if I rotate it, I can rotate it by 72 degrees 5 times, and it's going to be carried back onto itself. So that means the order would be 5. I can rotate this 5 times, 72 degrees, to carry the pentagon back onto itself. So the answer would be 72. Okay, looking at the last problem, it says a rhombus is graphed on the set of axes. Which transformation would carry the rhombus onto itself? All right, so knowing the properties of a rhombus, I know a rhombus has 4 congruent sides. And given the options that you had, the only option that makes sense in order for me to fold this rhombus onto itself would be to reflect it over the y equals 0 line. So the y equals 0 line simply is the y-axis. And I know that to be true because I already see 2 of the points directly on the line. So remember, if you have a point on the line of reflection, that point is equal to the image point. So we already have 2 points set and done. The only other point that I would have to look at is this point here on the left, which I see is 1, 2, 3, 4 units away, and this point here on the right, which is also 1, 2, 3, 4 units away. So if I reflect this point on the right over to this point on the left, I would have the same exact point. So that means that the only line of reflection that maps or carries the rhombus onto itself would be the y equals 0 line. All right, ladies and gentlemen, so that concludes our review for today. Please make sure that you are now going back to your long-term memory review, which is in your OneNote class notebook. Scroll down and you should see 8 questions that pertains to the review of transformations. Once you've completed that, you have Part D quizzes assignment that is also available to you to start working on. Have a great day, guys, and I'll see you next week.